So we are going to analyze the graphs of polynomial functions. Polynomial functions are a key way of graphing anything that is beyond a quadratic. So we're going to look at cubics, we're going to look at fourth roots, and fifth roots. To graph a polynomial function, we're going to first make a table. So our tables are going to be plugging in basic, large, numbers near the origin and focusing on just graphing those. After we make a table, we will plot the points from that table. After we plot those points, we will then make sure that our table meets the needs of our function, meaning if it is a fourth root, does it end in the same general behavior? If it is a odd function, does it start low and go high, or start high and go low, depending on the leading coefficient, etc. So that's why prior to today, we looked at leading coefficients. So when we start with all of our graphing problems, the first thing we're going to do is look at that highest powered term and look at its leading coefficient and degree to know if it's even, odd, and then positive or negative. So what are polynomial curves? Polynomial curves have to be smooth and continuous. So I say polynomial curves are like a roller coaster. You can't have a roller coaster that has an impossible curve or has a jump. So polynomial curves are like roller coasters. They have to be smooth and continuous. No one wants to ride a roller coaster that is not. So a smooth curve is a curve that does not have a sharp corner. A graph we looked at this year that has a sharp corner would be an absolute value. A graph we looked at this year with a sharp corner would be an absolute value. An absolute value is not a polynomial. So both of those graphs on your handout are non-polynomial graphs. So both of those graphs are graphs that are not polynomials. And these are the reasons why they're not polynomials. That first graph is not a polynomial because it has a sharp corner. The second graph is not a polynomial because it is not continuous. In order to graph that second graph, I have to pick up my pencil. I cannot connect them as one. So an example of a graph that's not a polynomial would be a piecewise. So piecewise functions are usually not polynomials because you're piecing two functions together, and usually when you piece two functions together, they're not smooth. Make sense? Again, both of those are examples of non-polynomials. The location principle says that if a value of f of x changes signs, if a value of f of x changes signs from one value of x to the next, then we can say that there is a zero between them. If the value in the table changes signs, then we can say there is a zero between them. We looked at this with quadratics. When we made our tables, and we said, oh, there's a zero between this number and that number because it goes from negative to positive, or it goes from positive to negative. A formal name for that is the location principle. The location multiplication principle simply says if your table changes from positive to negative or negative to positive, then there must exist a zero between them. And that all goes back to the fact that polynomials are smooth, continuous curves. If it was not continuous, you couldn't guarantee that. So now we have a function, and we have the function negative x to the fourth plus x cubed plus 3x squared plus 2x. The leading coefficient is negative. The leading coefficient is negative. The highest power degree is 4. So again, I'm looking at this negative and this 4. That tells me that my function is even and negative. Because of that, I know what the end behavior will look like. I know that as x goes to both positive and negative infinity, my function is going down in the ground. Because it's negative leading coefficient. So because it's an even with a negative leading coefficient, both of my graphs at the end should be pointing down. So no matter what this table tells me, I know that this graph needs to end with 2 arrows pointing down. I know that. That's what end behavior tells me. What we're going to do is plug in these numbers here. The easiest number to always plug in is 0. If every term has an x, then this answer is 0. That also means that 0 is a root. Perfect. 0 is a root. It is an x-intercept. So I could go over to my graph and I could plug point 0, 0. Because I know that this graph is going through 0, 0. Now I want to plug in my other numbers. So we're going to plug in -1, +1, -2, 2, 3. You don't, for now, there may come a time where I make you graph 1 by hand, but for now, use your calculator. It is your friend. So I'm going to show you how I would plug these in. You have 2 kind of choices. All right. So the first thing you could do is take your values and you could simply type out the function. So you could type negative parenthesis, -2 parenthesis, 4th power plus -2 3rd power plus 3 -2 squared plus 2 -2. Like that is one option. So everywhere you had an x, replacing it with a -2. Your second option
is instead of putting all the values here, you could have put the x there. And then, well, don't look at this answer because I don't know what it's plugged in. What you do is you say, okay, I want to know when x is -1. So I'm going to press on -1. I'm going to hit this button right here that says STO. That stands for store. So I'm going to click that button. And what it's going to do is type that -1 and an arrow on my screen. And then I'm going to press the X. And what it does is that puts an X value of -1 in. And then if you didn't know, you can go up and copy that and then hit enter. And what it's going to do is everywhere there's an X, it plugs in -1. And then you could do it again. So you would hit like 0, even though we already know this. Store X. Highlight, enter. And it would store 0 in for X. And you get 0. You can also go up and just like highlight and type on top of anything you already had. So I could type a 4, a 1, a 2, anything I wanted. To me, this is harder because you have to go backwards in time and kind of make sure you hit every number with a new number, as opposed to just saying 2, STO, X, enter, highlight, enter. Okay. So that gives you the following completed table. And then at this point, all you want to do is plot those points on your graph. So again, connecting those dots, I see exactly what I was hoping to see. It's even because both endpoints are pointing down. It has 2 x-intercepts. So even functions will have an even number of x-intercepts. Even functions will have an even number of x-intercepts. What this means is that I have 2 real and 2 imaginary. Since it only crosses twice, I have 2 real and 2 imaginary. So like when we did quadratics, it was like 0, 1, or 2. That 1, even though a quadratic is even, I always told you when you got that 1, it was a repeated root. So anytime it touches but doesn't cross, it is a repeated root. It means that intercept has a multiplicity of 2. Multiplicity of 2. Everybody okay with their graph? Let's do another one. Because 1 is never sufficient. We need to ensure we can do these. So we have a function who is raised to a power. So it is x cubed minus 4x squared plus 3x plus 1. So again, going back to what I just said, if it's an even degree, it will have an even number of intercepts. If it is an odd degree, then it will have an odd number of intercepts. And the number of intercepts can be never greater than the power of the function. So this is a cubic, so it'll either have 3 or 1. You can never have more than 3 crosses, and it's impossible not to have 1 cross. Because odd opposites, so at some point one line has to go through. Okay, so it's x cubed. X cubed is odd. The leading coefficient is positive. So that means that this is going to start low and end high. It's going to start low and end high. That was easy. When x is 0, y is 1. When x is 1, -1. -1. We get a -3 and -1, so -4, -5, -4 is -8. Okay? So 2 cubed is 8, 8 plus 1 is 9. 2 and 3 is 6, 15, 15 minus 8. 15 minus 16 is -1. I don't know. 64 minus, well, 64 is 0. Actually, 4 was easy. So we have -7, 1, 1, -1, 1, 13. So we have a table full of 1s. But what happens is every time there is a sign change, that implies that there is a 0. So from -1 to 0, the y's go from -7 to 1. So that means that there is a 0 or a root between -1 and 0. There is a root between 1 and 2, and then between 2 and 3, because the table once again changes sign. So from that graph, we see all of those betweens. We see all 3 roots. 1, 2, 3. We see that it ends high and started low. And then the last thing we're going to talk about is the number of extrema. The number of extrema will always be 1 less than the degree of the coefficient, of the leading coefficient. So in this case, our leading degree is x cubed. We have 2 extremas. We have a max and a min. So we have 2 extremas. So an extrema is simply a way of describing either a max or a min. So extrema means extreme values. So you will see or hear reference to an extrema. An extrema is an extreme value. The word relative is kind of like the word local. The word relative is kind of like the word local, meaning that it is the relative min to what is around it. Obviously, if this graph is continuing downward forever, it is not the lowest number on the graph, but it is the lowest number in that area. So relative is kind of like the word local. It means it's the lowest point in that area. And then the last thing I'm going to do is teach you how to find how to find mins and max on your graphing calculator. So the last thing we're going to do is find a min or a max on your graphing calculator. So go back to that calculator, go to y equals. So you're going to turn your calculator on, you're going to go to y equals. You're going to make sure that your plots are off. So what you want to do is type that function in y equals. Type that function in y equals. If you want to turn your plots off, arrow all the way up and hit enter on like the word plot 1 or plot 2. So you want to make sure that those plots at the top are not darkened. Yep. Okay. Zoom 6 is what they call zoom standard. It will graph your function from -10 to 10, -10 to 10 on all bounds. So if your graph is something crazy or off-centered, just hit zoom 6. Sometimes my graphs are in weird spots from different classes. Thinking really hard. All right, so we can see this is a cubic, right? Leading degree was a +2, so it starts low, goes high. I have 3 x-intercepts, 1 max, 1 min. To find the value of the max or min on the graphing calculator, you're going to hit second trace. And you're going to notice that it has min and max as an option. You need to make sure you select the right one for what you are finding. So if I want to find my max first, I'm going to hit option 4. And I have to move my cursor to the left when it says left of the max. I have to move it to the right when it says right of the max. Your guess means nothing. You can leave it where it is. So this graph has a max at -1, 1. Same idea, go to second trace. Now I'm going to do the min. I'm going to put it to the left, to the right. Whatever these arrows are pointing at, it's going to find the minimum between those dotted lines. If there's more than 1 min, it's going to struggle to find it. So you have to make sure, you're inclusive of what you're looking for. And this min is at 0.6 repeating, so that's 2/3, and then -3.629. So I worked through your homework. I gave you, so that bottom thing is just a graphic that kind of helps with vocab and what we're doing. I went through and I filled in all of the table numbers for you. So all you have to do is plug them in and plot your points. I also, because it was a textbook assignment, changed the graphs
or gave you hints on what your graphs need to go by. That way everybody's homework kind of looks the same tomorrow when I put up my answer keys. So I did kind of adjust it. You're just doing those 8 graphs. You're not doing like that one from on that page. We're going to do that together as a class. I know it kind of looks in the same font as the homework because I copied it over. So just do those 8 graphs for tomorrow. Yes.